This video explains the inbuilt NetSim experiment for simulating and comparing the mathematically derived TCP throughput against simulation. We are using NetSim version 12.1. Open NetSim, click on Example and navigate to Mathematical Modeling of TCP Throughput Performance, Sample 1. This loads the saved scenario. There are two nodes, connected via two routers on each end. The average throughput performance of the TCP congestion control algorithms can be approximated by the ratio of the average congestion window, CWND, and round-trip time, RTT. We consider two kinds of networks: a lossless network and a lossy network. In a lossless network, we can expect the TCP congestion window, CWND, to quickly increase to the maximum value of 64 kb, without TCP scaling. Then the average TCP throughput can be obtained by the formula shown on the screen. In a lossy network, the congestion window may be approximated to increase from an average value of W/2 to W. The throughput can be approximated to vary from W/2 by RTT to W/RTT. Then the average TCP throughput can be obtained by the formula shown on the screen. Now let us see NetSim example simulation settings. In the first sample, we set up a simple constant bit rate, CBR, application between the source node, node 1, and destination node, node 2, with packet size set to 1460 bytes, and inter-arrival time set to 1168 microseconds to get a generation rate of 10 Mbps. The link properties are set such that max uplink and downlink speed for all three links are set to 10 Mbps each. The link bit error rate is set as 0. The propagation delay, in the links between the nodes and the routers, is set to 100 microseconds. And the propagation delay, for the link between the two routers is set as 50,000 microseconds. Wireshark option is enabled by setting it as online in the source node. Now, set the simulation time to 100 seconds and click OK. After simulation, note down the application throughput. The graph shows the long-term average throughput plot of the TCP connection. The congestion window evolution graph can be obtained from Wireshark. Choose a data packet and go to Statistics, TCP Stream Graphs, Window Scaling. This is the congestion window evolution of TCP Neutrino, over a lossless link. Similarly, when we run sample 2, we modify the properties of the link between the two routers such that the bit error rate, BER, is set to 1 into 10 to the power minus 7. All the remaining properties remain the same as the first sample. Run the simulation and analyze the results. We notice a slightly lower throughput and higher delay. The plot for long-term average throughput of the TCP connection over a lossy link can be seen here. And this is the congestion window evolution of TCP Neutrino over the lossy link. We notice that the congestion window of TCP over the lossless link increases monotonically to 64 kb and remains there throughout the simulation time. So, a block of 64 kb of data is transferred over a round-trip time, RTT, of approximately 100 milliseconds. Hence, a good approximation of the TCP throughput over the lossless link is as shown on the screen. For the lossy link, with packet error rate P, the approximate throughput of TCP is given as shown on the screen. Where P is the packet error rate, MSS is the maximum segment size in bits and RTT is the round-trip time in seconds. The packet error rate P can be computed from the bit error rate and pi layer packet length as shown on the screen. We note that the observed long-term average throughput for a lossless link is approximately equal to the computed value. Similarly, the observed long-term average throughput for a lossy link is also approximately equal to the computed value. Thank you for watching.